In this video, I wanted to do an introduction to limits, notation, and different ways of finding them, starting with specifically finding limits both numerically and graphically. And as we progress through the semester, we're going to get into other methods of determining limits as well. So to begin with, the limit of a function is something that can be often referred to as the behavior of the function towards a particular position. Often we phrase it in a way where there's, like in an equation, we have a relationship between y and x. Like in the slides below, at the given example, we have the equation y is equal to 1 over x. It describes a relationship between the variables x and y. And a limit can often be a way of determining what is happening as x does something, what happens to y, sort of that same relationship. But limits are more specifically used for, typically describing values where the function is undefined. Because a limit, so a lot of the time, may have no differentiation between just the evaluation of a function, a particular value. So let's go ahead and talk about what we might refer to as end behavior or behavior towards an asymptote in this particular function. So let's go ahead and look at the example, let y is equal to 1 over x. Sometimes we may refer to this as the end behavior. As x approaches infinity, y approaches something. And this is a way you may have seen it before. And if not, let's go ahead and discuss what this means, because the way a limit is defined is analogous to this. So basically, in mathematics, this arrow symbol, let me find my pen. Sorry, let me try to get my pen working. I can't seem to get it. There we go. The arrow in mathematics is often referred to as approaches or trends towards. So, or heads towards is kind of a way you could think about this. But how I'd read this is as x approaches infinity, y approaches blank. So here it's kind of a fill in the blank because I wanted to practice identifying the behavior in particular positions. But basically, a lot of times limits are used for describing what happens as x trends towards a value that it's not defined at. Like for example, infinity is not a number. It's not something where we could plug it in for x and say, well, okay, in this case, 1 divided by infinity would be the replacement. Kind of like if we had let x equal 2. Well, then y would be equal to 1/2. Or if x was equal to 7, y would be equal to 1/7. In most contexts, we can take a function or equation and simply plug in the numbers as we need to. But limits are often used to understand positions where we can't just do that, where the function may be undefined. Technically, you can do a limit anywhere, but often we do it at stranger places, such as infinity. But the thing about infinity is it's not a number. This is not an expression. We are not allowed to plug it in because it's not part of the domain. It's the idea of if there were a largest possible number in math, that this would be the description of that. But there is no number that's the largest because you can always come up with a larger number. Anyways, how we can interpret this, if we're looking at a limit graphically, we could kind of look at this sort of function where 1 over x is sometimes referred to as the reciprocal function. Because if you plug in larger and larger numbers, say for example 2, what we'd end up with is 1/2. Or if we plug in 3, 1/3, 4, 1/4. Basically, it's going to get smaller and smaller and smaller because larger and larger numbers mean smaller and smaller fractions. And so as x approaches infinity, basically as x gets larger and larger, like on the number line, any Cartesian coordinate graph with an xy axis, you can think about what's happening in a specific direction. Like as x approaches infinity, I would literally think about, well, this is the x-axis. As it's going to infinity, that means to the right. Technically, if I were to go forever, it's not just about what's happening at, say, 10, the end of the domain in this graph. It's more about what's going to continue happening literally forever. That's, the idea of infinity. But certain functions have trends, they have patterns. And in this case, we sometimes call it, well, the end behavior. And as x gets larger and larger, what's happening to the value of 1 over x, or what's happening to y, it's getting smaller and smaller, right? Because it's going 1/2, 1/3, 1/4. And if this continues, basically I could imagine plugging in a larger and larger number in for x in the denominator, like 100 or 1,000. And this is more akin to what we refer to as a numerical approach to finding a limit. Very similar to graphical, but at the end of the day, what's happening is it's getting smaller and smaller. It's getting closer and closer to 0 because the value of where the y-axis, meets the x-axis is the origin 0, 0. And as x trends to infinity, the value of y, or the function, it's getting closer and closer to the x-axis, is going towards 0. And so what we would say is that as x trends to infinity, y tends to 0. Or, again, using the notation, as x approaches infinity, y approaches 0. And sometimes you could technically be more specific and say x approaches 0 from above because it's happening above the axis instead of below the axis. A distinction which is usually not relevant and not needed, and I wouldn't typically make that distinction myself. But in some contexts, I've seen people write that. And similarly, let's say we were thinking about what happens as x approaches negative infinity as the end of an infinite limit, and we'll define and talk about this more in the next video. But basically, on the left-hand side, as x approaches negative infinity, again, how I kind of think about it is, well, this is x approaching negative infinity. Now, if I want to know what is happening to y, I could trace along my equation or my curve, again, with a graphical approach, and say, well, it is also getting closer and closer to 0 in the same way that it is on the right-hand side. But in this time, you could say it's heading to 0 from below rather than from above, where I'll talk a little bit more about what that little plus and little minus means in just a second. And so additionally, another case where the reciprocal function is a little strange is at 0. Another thing, and this is probably a math thing you've heard before, is, well, what happens to 1 over x if you plug in 0? Like, what does dividing by 0 mean? How do I do this? Is it 0 or what? And this is something where you probably have heard before. Dividing by 0 is not allowed. We say it's undefined. It's not a number. And there's a lot of different ways to remember that. The way I often think about it is, let's say you have, I like to use this example. Let's say that you have 6 friends and $0. Well, if you have $0, you can divide up your vast wealth to your 6 friends. You can share everything, and basically everybody's going to get $0, right? 0 can divide into 6 because it makes 6 groups of nothing. Divisibility of 0, it just results in nothing. It's totally fine, and it's a defined operation. Kind of like when you multiply anything by 0, you get 0 because you're putting it into 0 groups conceptually. However, if you flip this situation, if you have $6 but you don't have any friends, you can think about trying to divide up your wealth to your friends. $6. Well, how can I break $6 into 0 groups? It doesn't make sense to be 6 because I'm trying to divide it to my friends and share it with them in this situation that I'm just making up. And I can't give out money to my friends if I don't have any friends. It doesn't make sense to be 0 either because 6 will not divide into groups of 0. It doesn't make sense. So instead of being defined as 0, it just is an undefined operation. But another point of limits here is trying to shed light on this situation of, well, you can't divide by 0. It's true. Like, you're not allowed to use 0. We often refer to this as saying 0 is not in the domain of this function. And if we look at the graph, you can see that there's this weird jump. Discontinuity is what we call it in calculus in the function, where it's sort of going from the left down up to the right, looking at its graph. But if we examine the limit towards 0 from both the right hand side and the left hand side, we can see that there's kind of it's a different pattern. Like, looking at it from the left hand side going downward, basically if I get closer and closer to the value of x is equal to 0, and that's again what this would read here, as x approaches 0, I wanted to also elaborate, what does this little plus mean, and what does the little minus mean? But basically, the little plus in the exponent and the little minus in the exponent over here stands for from the right and from the left. So like reading this one right here, I would read this as x approaches 0 from the left hand side, and why negative is left is because that's the negative side of numbers. And so, like, when I'm looking at the graph over here as it comes downward, basically this is from the left hand side. I'm getting closer and closer to 0, which oftentimes I might refer to this as the wall method, and I'll talk about this again in a later video. You can think about, where is 0 on the graph? X is equal to 0 would be right there. Basically the y-axis would be a wall through x is equal to 0. And if I try and examine a limit towards 0 from the left-hand side, which is what this part is saying right here. Sorry, it's cut off a little bit because of my frames. I would be looking at what's happening to the function as it gets closer and zero, as it gets closer and closer to 0 from the left-hand side. And in this case, it's going downward further and further, and it appears to be going down unrestricted towards minus infinity. In this case, we'd write the limit as negative infinity because it's unlimited. Or again, I could kind of think about that as, well, what if I were to plug in numbers, which would be a numerical approach? Let's say what I would want to think about numbers getting very, very close to 0, such as maybe 0.1, 0.001, and thinking about, well, what would happen to the reciprocal of such a number. And again, if I'm looking at a graph, it's jumping down very, very quickly. It's ascending vertically downward, and it will be unrestricted. It's a little bit easier to understand this in a numerical sense. So we'll revisit these. Sorry, this is kind of a hard example to start with, but I'm just trying to introduce a lot of the meaning of these symbols. It's not about understanding this specific example yet, because we'll elaborate. And so the difference between a left-hand limit and a right-hand limit is, well, if I look at what's happening towards 0 from the right-hand side, it's actually different, right? Because on the right-hand side, it's not going down, it's going up instead. And we can see that it's going to be going up vertically in an unrestricted fashion. It's headed towards positive infinity on the y side. So as x approaches 0 from the right, which is again how this reads and what this means, again, plus right-hand side, negative left-hand side. It's kind of like, well, the negative side is the left-hand side of the graph, the positive side is the right-hand side. And why is it in the exponent? Well, there's not really a good answer to that. It's just a notational thing. It doesn't mean an actual exponent like 4 to the third power. Anyways, in this case, these are all ways of describing the behavior towards infinity and towards a vertical asymptote. Now, with certain types of functions, we call these lines asymptotes. We'll define that in a little bit. But anyways, I wanted to introduce those ideas in this first video. In the next video, we'll do more specific examples of numerical and graphical limits.